We can use the atomic orbitals on a set of atoms to form a basis for a reducible representation, and then we can decompose that reducible representation into irreducible representation. But it still leaves the question open as to how we actually construct a basis set that is a linear combination of those atomic orbitals that have the appropriate symmetry properties. The way we do this is using something called generating operators. Now, I'm not going to necessarily develop these from first principles, but what I want to do is at least show you what the definition of a generating operator is and how it works. So for example, the generating operator for a particular irreducible representation, so what we're doing is we're taking a set of atomic orbitals, and from them we want to generate an linear combination of them that has the particular irreducible representation indicated here. So that would be J, and that's going to be equal to the dimensionality of that irreducible representation over the order of the group times the following operator. We're going to sum over the various operations of the group, use the characters of those operations for the ith irreducible representation, times the operator itself, the symmetry operator, on our basis function. All right, so in order to illustrate this, I want to go back to our butadiene example, and I've reproduced some of the things that we've seen in other videos here. Here is the molecule. It's lying in the sigma H plane. The center of the molecule is the inversion center. That's also the point where the axis of rotation, the C2 axis, intersects the plane of the molecule. We've numbered the 4 carbons starting on the left, 1, 2, 3, and 4. And we're implicitly looking at a basis now that is the PZ orbitals on each of these carbon atoms. Now, rather than reproduce again the actions of these various operations on the various 2pz orbitals, I've created a table down here to summarize it. So in other words, if I start with the 2pz orbital on atom 1 and I use the identity operation, I will get that same orbital back. I will get, under the C2 operation, I will get the pz orbital that corresponds to atom 4. If I use the inversion operation, I will get the negative of the pz orbital on atom 4, and if I use the reflection through the sigma H plane, I will get the negative of my original orbital. And this same sort of thing goes through for all 4 of these pz orbitals as they're listed here going down. All right, so now how do I apply this generating operator to get a result? I suppose it's worthwhile to summarize also that when we did our analysis on butadiene, we found that the reducible representation for the 2pz orbitals was equal to 2bg plus 2au. That is, we're going to have 2 linear combinations that have Bg symmetry and 2 that have Au symmetry out of the 4 that we can generate. And this is one reason why I've sort of shaded out 2 of the rows in the character table. We only need these 2 rows to do what we need to do with the projection operator. Okay, so how do I project these things out? So now let's suppose that I'm going to project out a Bg The PG projection operator would look like this. Okay, the dimensionality of all of our irreducible representations is 1, so we'll always have 1 up here, and the order is always 4. So we'll always have 4 there. So now when I use BG, I'm talking about taking this character times the operation of each of these elements, for example, on Phi1. So I'll have the sum of 1 times Phi1, representing the operation of the identity operator on Phi1, plus the character of C2, which is, it's going to be 1 is the character of C2 times the Phi4, which is the result of making that operation. And then I'll have plus So the projection of a linear combination that has BG symmetry would look something like this. The dimension of all my irreducible representations in this point group is 1. The order is 4, so this will be true of all of our projection operators. And then I'm going to take the product of the character that's listed here in the table times the result of the operation of each of these symmetry operations on a particular basis function. So in this case, I would have 1 times phi1 minus 1 times phi4 plus 1 times minus phi4 minus 1 times minus phi1. And I think when we get through with all of this, we'll end up with 1/2 of phi1 minus phi4. All right, so what we've done is we've been able to use this projection operator on one of our basis functions, phi1, to generate a symmetry-adapted linear combination, phi1 minus phi4. Now, don't worry too much about this number out here. It does come out of this calculation, but this would not be normalized with that. In fact, the normalized version of this will be 1 over the square root of 2 phi1 minus phi4. All right. But this is the result of using the projection operator. Now, if I were to use the projection operator on function 2, I would, with a very similar sort of development, I would end up with phi2 minus phi3. And you can see that these do not involve the same functions. They are distinct from one another. And so these represent the two different linear combinations that have BG symmetry in our symmetry adapted basis here. All right. I could then also operate my generating operator on phi3. I would end up getting 1/2 phi3 minus phi2, but because this only differs by a sign from this one, we consider these to be the same result. Similarly, if I generated a generating operator operating on phi4, I would get the negative of this one. So these are the only two unique results that I'll get from using the generating operator with symmetry BG on this basis. What about symmetry AU? All right, well in that case, and I'll use a different color to distinguish them, for symmetry AU operating on phi1, I'll again have 1/4, and then I'll have each of these characters times the results of the operation. So, for example, I'll have 1 times phi1, I'll have 1 times phi4, I'll have minus -1 times phi4, and minus -1 times phi1. So the net result of this is phi1 plus phi4. And you can see that it is, again, distinct from what we got here for BG. It involves the same two atomic orbitals, but it is a different symmetry-adapted linear combination. I think it's probably easy to see, or I hope it is by now, that if I do this same thing for phi2, I'll end up with phi2 plus phi3. So here I have 4 different linear combinations, phi1 minus phi4, phi3 or phi2 minus phi3, phi1 plus phi4, and phi2 plus phi3, which represent my different symmetry-adapted linear combinations of these atomic orbitals.